Welcome to Sleeping Researcher, your peaceful haven where science narration gently guides you into restful sleep. Tonight, we will embark on a serene journey through the vast cosmos, exploring how humanity harnesses the energy of stars. From the familiar glow of sunlight captured by photovoltaic cells, to the cutting-edge ideas of future energy sources like nuclear fission, and even the awe-inspiring concept of Dyson spheres, massive structures built to encircle stars and capture their boundless power. Our story unfolds at the intersection of science and imagination. As we explore these fascinating advances, allow your mind to drift with the quiet wonder of the universe. Before we begin, if you find comfort in these calm scientific tales, please like this video and subscribe to Sleeping Researcher. Your support helps us continue to share soothing explorations of science designed to ease your mind and enhance your sleep. Now, settle in comfortably as we gently illuminate the remarkable ways stars light our present and future, offering not only energy, but inspiration to dream beyond the stars. From the earliest days of human existence, the pursuit of energy has been a silent companion to our progress. Fire, the first harness source, illuminated our nights and warmed our shelters, symbolizing the dawn of civilization. Today, as we stand on the threshold of the future, our energy needs have grown exponentially, fueled by expanding populations, technological advancements, and an insatiable desire for comfort and connectivity. This relentless demand compels us to seek solutions that are not only powerful but sustainable, ushering in an era where the stars themselves become more than distant points of light. They become potential allies in our quest for energy. Solar energy, directly captured from the sun's rays, represents the most immediate and abundant source available to us. Photovoltaic cells, which convert sunlight into electricity, have transformed vast swathes of sunlight into usable power, enabling everything from small electronic devices to entire cities to function sustainably. These silicon-based devices have steadily improved in efficiency and affordability, marking a significant milestone in renewable energy technology. Yet, while solar panels capture only a fraction of the sun's immense output, they hint at the vast potential locked within our star's radiation, inspiring scientists and engineers to imagine even more ambitious methods to harness this celestial energy. Looking beyond photovoltaic cells, the exploration of nuclear fission and fusion represents the next frontier in energy production. Unlike solar panels that rely on the sun's light, these processes tap into the atomic forces that power stars themselves. Nuclear fission, already in use in many parts of the world, splits heavy atoms to release energy, offering high-density power with relatively low emissions. Fusion, the process that fuels stars by combining light atomic nuclei, promises an even more powerful and cleaner energy source, though it remains a complex challenge to achieve sustained reactions on Earth. These advancements embody humanity's aspiration to mimic the very processes that sustain stars, moving us closer to a future where energy is abundant, safe, and sustainable. Farther into the realm of theoretical and futuristic concepts lies the notion of Dyson spheres, vast megastructures envisioned to envelop entire stars, capturing their energy output on an unprecedented scale. Proposed by physicist Freeman Dyson, these colossal constructs symbolize the ultimate ambition to harvest stellar energy, transforming it into a resource that could power civilizations far beyond our current capabilities. While purely speculative at present, the idea encourages us to think boldly about our place in the cosmos and how we might one day engineer solutions that transcend the limitations of our planet. It is a testament to human creativity and determination, pushing the boundaries of what is possible in the pursuit of energy that endures. As we reflect on this journey, from the humble beginnings of firelight to the prospect of constructing star-encircling habitats, we recognize a continuous thread of innovation and hope. Each step forward brings us closer to unlocking the vast energies contained in the stars, promising a future where energy scarcity is a relic of the past. This ongoing quest invites us to explore not only the technologies that will power tomorrow, but also the wisdom to use such power responsibly. With this foundation, we now turn our attention to the specific technologies that are shaping the immediate future of stellar energy capture, beginning with the ever-evolving field of photovoltaic systems. The sun stands as the enduring heart of our solar system, radiating an immense and steady flow of energy that sustains life on Earth. This vast celestial furnace, powered by nuclear fusion deep within its core, emits light and heat that reach us across the void of space. For millennia, humanity has relied on this natural gift, harnessing its warmth to grow crops, maintain ecosystems, and illuminate our surroundings. Yet the sun's role as an energy source extends far beyond these simple, life-giving functions. Modern science and technology have given us the means to capture and convert sunlight into usable energy forms, enabling us to tap directly into this abundant resource. Photovoltaic cells, commonly known as solar panels, exemplify this transformation. By converting photons into electrical current, these devices provide a clean, renewable, and increasingly efficient way to power homes, industries, and even entire cities. The quiet, steady energy of the sun thus forms the foundation of a sustainable future, inviting us to reimagine our relationship with the natural world and the cosmos. Photovoltaic technology, though relatively young in the span of human history, has advanced rapidly. Early solar cells were modest in efficiency and costly to produce, limiting their widespread adoption. However, continuous improvements in material science, manufacturing techniques, and design have led to panels that are more efficient, durable, and affordable. Today, these solar cells are integrated into rooftops, solar farms, and even portable devices, symbolizing a shift toward decentralized energy production. Beyond conventional silicon-based cells, research explores novel materials such as perovskites, which promise even greater efficiency and flexibility. This progress reflects a broader vision of energy independence and environmental stewardship, where the sun's energy is no longer confined to passive warming, but actively drives our technological society. Yet, capturing sunlight at the surface of our planet represents only the beginning of what might be possible. The boundless energy of stars, including our own sun, holds potentials that extend far beyond current methods of harnessing light. Looking further into the future, humanity's quest to utilize stellar energy may transcend photovoltaic conversion, venturing into more complex and powerful technologies. One such possibility lies in the domain of nuclear fission and fusion, processes inspired by the very reactions powering the sun. While fission, the splitting of heavy atomic nuclei, has been a source of energy on Earth for decades, fusion, the joining of light nuclei, remains an aspirational goal. Fusion holds the promise of nearly limitless, clean energy, mimicking the sun's core processes on a controlled scale. Achieving practical fusion energy could revolutionize our energy systems, enabling sustained power generation with minimal environmental impact. Beyond terrestrial applications, envisioning structures that capture the full energy output of a star leads us to the concept of megastructures, such as Dyson spheres. These hypothetical constructs would envelop a star to harness its immense energy, potentially providing power on a scale unimaginable today. While still theoretical, these ideas inspire us to think boldly about our place in the universe and the ways we might one day thrive by embracing the stars themselves. The notion of capturing stellar energy on such grand scales invites profound reflection on both technological possibility and philosophical responsibility. Constructing devices like Dyson spheres would require unprecedented advances in materials science, engineering, and energy management, as well as a deep understanding of the environmental and ethical implications of manipulating stellar phenomena. It challenges us to consider not only how we might extend our reach into the cosmos, but also how we might preserve the delicate balance of cosmic systems. In this light, the sun's energy is not merely a resource to be exploited, but a symbol of continuity and harmony between humanity and the universe. As we continue to innovate, the integration of emerging technologies such as advanced photovoltaic systems, nuclear fusion reactors, and fissionary megastructures will shape our future energy landscape. Each step forward must be guided by wisdom, ensuring that the immense power of stars serves the well-being of all life. As we contemplate these evolving technologies and their potential to redefine energy generation, we return our focus to the immediate horizon, where photovoltaic advances continue to lead the way. These systems, already integral to sustainable energy strategies worldwide, set the stage for more ambitious endeavors. By refining the efficiency and scalability of solar energy capture, we lay the groundwork for integrating complementary technologies such as energy storage, smart grids, and eventually fusion power. The journey from capturing sunlight on Earth's surface to harnessing the full might of the sun challenges us to blend innovation with thoughtful stewardship. With this understanding, we prepare to explore in greater detail the specific technologies shaping the near future of stellar energy utilization, beginning with the ever-evolving field of photovoltaic systems. Photovoltaic cells, commonly known as solar cells, represent one of the most elegant and direct methods of converting the sun's abundant energy into usable electricity. These cells are made from semiconductor materials, most often silicon, which possess the unique ability to absorb photons, packets of sunlight, and release electrons as a result. This phenomenon, known as the photovoltaic effect, allows the generation of an electric current without any moving parts or emissions. The simplicity and reliability of this process have made solar panels an increasingly prominent feature in energy systems around the globe. By capturing sunlight during daylight hours, photovoltaic arrays can supply clean, renewable energy to homes, businesses, and even entire communities. This technology continues to evolve, with ongoing research focusing on improving efficiency, reducing manufacturing costs, and developing flexible or transparent solar materials that could seamlessly integrate into everyday surfaces. The widespread adoption of photovoltaic technology is not only a testament to human ingenuity, but also a critical step toward reducing our reliance on fossil fuels. In many regions, solar power has become economically competitive with traditional energy sources, supported by advances in energy storage solutions such as batteries, which help manage the variability of sunlight across day and night cycles. Smart grids further enhance this dynamic by optimizing energy distribution based on demand and supply fluctuations. These systems, working in tandem, provide a glimpse of a sustainable energy future where the sun's rays are harnessed efficiently and responsibly. Moreover, the modular nature of photovoltaic installations allows for scalability, from small rooftop panels to large solar farms spanning hundreds of acres. Each installation represents a building block in a global effort to transition toward cleaner energy landscapes. Yet, as promising as these developments are, they also serve as a foundation upon which more ambitious technologies may rise. Looking beyond the horizon of photovoltaic cells, the quest to tap into stellar energy leads us to contemplate more advanced methods, including nuclear processes such as fusion. Fusion energy, inspired by the very reactions that power stars, holds the potential to deliver immense amounts of energy from relatively small amounts of fuel with minimal environmental impact. While still under development, fusion represents a profound leap in our ability to harness the sun's power, moving from passive capture of sunlight on Earth to actively replicating the stellar furnace itself. This progression highlights the evolving relationship between humanity and the cosmos, a journey from simply receiving energy to mastering its generation. As research continues, fusion may one day complement or even surpass photovoltaic systems, offering a nearly inexhaustible energy source that aligns with our aspirations for sustainability and abundance. In an even more visionary context, the concept of Dyson spheres invites us to imagine civilizations capable of encompassing entire stars to capture their total energy output. Proposed as a theoretical megastructure, a Dyson sphere, or more realistically, a swarm of solar collectors orbiting a star, could harness energy on a scale far beyond current terrestrial technologies. While such constructs remain speculative, they inspire ongoing discussions about the future of energy utilization in the cosmos. The principles underlying photovoltaic cells are fundamental to these grand designs, as each collector would convert stellar radiation into usable power for interstellar civilizations. Exploring these ideas challenges us to expand our understanding of engineering, materials science, and energy management, pushing the boundaries of what is conceivable. As we refine solar technology here on Earth, we also nurture the seeds of these far-reaching aspirations, blending science fiction with emerging scientific possibilities. Thus, from the familiar rooftops adorned with solar panels to the distant dreams of harnessing entire stars, the journey of using stellar energy unfolds. Photovoltaic cells remain the foundational technology, steadily evolving and integrating into our energy landscape, while fusion research and speculative megastructures point toward future frontiers. This continuum reflects humanity's enduring curiosity and our commitment to harmonizing with the energy that sustains life itself. As we venture further into these realms, the next chapters will delve deeper into the advancements propelling fusion energy and the visionary concepts that stretch our imagination beyond our planet. Photovoltaic technology, the cornerstone of modern solar energy, has witnessed remarkable advancements over recent decades. Traditional silicon-based solar cells, once limited by relatively modest efficiencies, have gradually given way to more sophisticated designs that capture sunlight with increasing precision. Among these innovations, perovskite solar cells have emerged as a promising candidate, offering the potential for higher efficiency at lower production costs. Their unique crystal structure allows for excellent light absorption and charge transport, making them a flexible alternative to conventional materials. Researchers continue to refine their stability and scalability, moving closer to practical applications that could revolutionize solar energy accessibility. Alongside perovskites, multi-junction solar cells combine layers of materials, each optimized to absorb different wavelengths of sunlight, thereby surpassing the efficiency limits of single-junction cells. These cells, although currently more complex and costly, pave the way for specialized uses such as space exploration and concentrated solar power. This steady progression in photovoltaic technology reflects a broader trend of harnessing stellar energy more effectively, transforming the abundant sunlight into usable power with ever-increasing sophistication. Beyond the realm of photovoltaic cells, the pursuit of fission and fusion energy represents humanity's quest to mimic the processes that power the stars themselves. While nuclear fission has long been employed as a potent energy source, its association with radioactive waste and safety concerns has spurred interest in more advanced and cleaner alternatives. Fusion, the process of merging atomic nuclei to release energy, promises an almost limitless supply of power with minimal environmental impact. Though still in the experimental stage, fusion reactors like tokamaks and stellarators aim to recreate the conditions found in the cores of stars, where immense pressure and temperature enable this reaction. Progress in magnetic confinement, plasma stability, and material science steadily brings fusion energy closer to reality. achieving controlled fusion on Earth would mark a profound leap in energy generation, complementing the sunlight captured by photovoltaic cells with a stellar process brought to earthly application. This convergence of technologies underscores humanity's drive to tap into the fundamental forces that illuminate our universe. Gazing further ahead, visionary concepts such as Dyson spheres capture the imagination, proposing a future where entire stars could be harnessed as sources of energy. Originally theorized as a swarm or shell of energy collectors enveloping a star, a Dyson sphere would represent the ultimate scale of stellar energy utilization. Although currently a theoretical construct, this concept challenges our understanding of engineering, material science, and energy management. Constructing such a megastructure would require unprecedented advances in robotics, resource extraction, and orbital mechanics, as well as sustainable methods to balance the delicate gravitational and thermal forces involved. The idea stimulates ongoing discussions about the potential for advanced civilizations to utilize their stars' full energy output, inspiring both scientific inquiry and speculative fiction. While practical realization remains distant, the underlying principles encourage exploration of scalable energy solutions beyond our planet and expand the horizons of humanity's energy aspirations. In the continuum from silicon panels on Earth to the cosmic scale of Dyson spheres, the evolution of solar technology embodies our persistent effort to align with the star that feeds life on our world. Each advancement, whether incremental or revolutionary, brings us closer to a harmonious integration with this vast energy source. The interplay of material innovation, nuclear physics, and visionary engineering forms a tapestry of progress that continues to unfold. As research pushes the boundaries of efficiency, stability, and scale, the promise of abundant, clean energy shines ever brighter. Yet, these achievements also pose profound questions about stewardship, sustainability, and the ethical use of such power. The narrative of solar technology is thus not only one of scientific triumph, but also of thoughtful coexistence with the cosmos. Continuing this exploration of stellar energy, we turn now to the emerging frontiers of fusion power, where the dream of replicating the sun's core processes inches closer to reality. The intricate dance of plasma particles and magnetic fields within fusion reactors offers a glimpse into the future of energy, one that may redefine our relationship with the cosmos and the stars that light our skies. While the sun provides a seemingly endless supply of energy, harnessing it from Earth's surface presents inherent challenges that temper its full potential. Photovoltaic cells, those elegant devices that convert sunlight into electricity, are fundamentally dependent on consistent exposure to sunlight. Yet, the natural rhythms of our planet impose limits. Weather patterns cast shadows, clouds obscure the sun's rays, and the daily cycle of night inevitably pauses solar energy collection. These interruptions mean that solar power generation fluctuates, requiring sophisticated energy storage systems or complementary power sources to maintain stability in our grids. Furthermore, seasonal variations in sunlight intensity demand adaptable technologies that can respond to ever-changing environmental conditions, reminding us that Earth's dynamic atmosphere plays a central role in shaping our energy landscape. Beyond the intermittent nature of sunlight, the physical footprint of solar energy infrastructure poses additional constraints. Vast arrays of photovoltaic panels require significant land areas, often competing with agricultural needs, natural habitats, or urban development. This spatial demand invites careful consideration of where and how solar farms are placed, balancing the pursuit of clean energy with ecological preservation and societal priorities. Rooftop installations and innovative designs offer partial solutions, integrating energy production into existing structures, yet scaling these efforts to meet global energy demands remains a formidable task. The interplay between land use and energy generation thus emerges as a delicate dance, one that underscores the complexity of transitioning to renewable energy on a planetary scale. As we look beyond present technologies, the quest for capturing stellar energy draws us toward more ambitious concepts. The limitations of Earth-based solar power inspire visions of harnessing energy directly from the stars themselves, not merely their light, but the profound forces that govern their existence. Nuclear fusion, the process powering our sun, holds promise as a clean and abundant energy source. If only we can master its intricacies within terrestrial reactors. Progress in magnetic confinement and inertial fusion experiments suggests that replicating stellar conditions on Earth may one day overcome the variability faced by photovoltaic systems. In this light, fusion represents a bridge between the sun's distant brilliance and our immediate energy needs, a synthesis of cosmic power and human ingenuity. Looking even further ahead, speculative yet captivating ideas such as Dyson spheres hint at a future where humanity could capture the total energy output of an entire star. These megastructures, theoretical shells or swarms enveloping a sun-like star, would collect energy on a scale that dwarfs all our current consumption. While engineering such constructs lies far beyond today's capabilities, the concept challenges us to imagine energy not as a terrestrial limitation, but as a cosmic resource to be tapped. This vision extends the boundaries of our energy ambitions from the surface of our planet to the vastness of space, inviting contemplation of how the stars themselves might one day become the engines of civilization. Thus, the journey from photovoltaic cells on Earth's surface to the tantalizing prospects of fusion and stellar megastructures charts an evolving relationship with the sun's energy. Each step reflects both the constraints we face and the boundless creativity with which we seek to transcend them. As our understanding deepens and technology advances, the dream of drawing power directly from stars continues to inspire, guiding us toward new horizons where energy and the cosmos intertwine. of the most compelling steps in harnessing stellar energy lies beyond the confines of our planet's atmosphere. Space-based solar power envisions satellites equipped with expansive photovoltaic arrays orbiting Earth, capturing sunlight in its purest and most uninterrupted form. Unlike solar panels on the ground, these orbital platforms are free from the limitations imposed by weather, atmospheric scattering, and the day-night cycle. This continuous influx of radiant energy promises a constant and vastly more efficient source of power. Once collected, this abundant energy can be converted into microwave or laser beams and transmitted wirelessly down to receiving stations on Earth. Such a system could fundamentally augment our terrestrial power grids, offering a clean and inexhaustible energy supply that circumvents many environmental and logistical challenges associated with conventional solar farms. Space-based solar power represents a fusion of advanced aerospace engineering and renewable energy technology, inviting us to reconsider where and how we gather the sun's gifts. This approach not only maximizes energy capture, but also inspires a profound reconnection between humanity and the cosmos, as our eyes and instruments extend upward to tap the light of our nearest star. The journey towards space-based solar power is marked by both remarkable progress and formidable challenges. Launch costs, efficiency of wireless energy transmission, and the durability of solar arrays in the harsh environment of space remain active areas of research and development. However, advances in lightweight materials, autonomous assembly techniques, and power beaming technologies are steadily turning these early visions into plausible realities. Moreover, the modular nature of these satellite arrays suggests a scalable energy system, one that could grow incrementally alongside humanity's expanding presence in space. By deploying such infrastructure, we begin to rethink energy not as a resource confined to the Earth, but as a universal commodity, accessible wherever sunlight falls. This paradigm shift could dramatically reduce our dependence on fossil fuels and terrestrial energy sources, mitigating environmental impacts while simultaneously fueling space exploration and settlement. The silent solar collectors orbiting above us might one day become the backbone of a sustainable, star-powered civilization. Looking further ahead, the aspiration to harness stellar energy invites us to imagine even grander technologies. Beyond photovoltaic conversion, the prospect of tapping into nuclear fusion, the very process that powers stars, offers a glimpse of energy generation with unparalleled density and cleanliness. Fusion reactors, still under experimental development, seek to replicate the sun's core reactions here on Earth, fusing light atomic nuclei to release vast amounts of energy without the long-lived radioactive waste of fission. Should these efforts succeed, fusion could provide an almost limitless energy source, bridging the gap between current capabilities and the vast power radiated by stars. This milestone would redefine our relationship with energy, enabling technologies and industries previously constrained by power availability and setting the stage for even more ambitious ventures beyond our solar system. Beyond fusion, visionary concepts such as Dyson spheres embody humanity's ultimate aspiration to capture and utilize the full energy output of a star. These hypothetical megastructures enveloping or surrounding a star with an array of energy collectors, represent a scale of engineering that transcends the planetary and even solar system boundaries. While still firmly within the realm of theoretical exploration, Dyson spheres symbolize our desire to move from merely receiving stellar energy to commanding it on a cosmic scale. The construction of such colossal structures would require unprecedented advances in materials science, robotics, and space logistics, as well as a profound understanding of stellar dynamics. Yet the very idea of harnessing a star's power in its entirety challenges us to rethink the potential of energy as a driver of civilization's evolution, inviting contemplation of what lies beyond the horizon of our current technological imagination. As humanity contemplates the grand ambitions of capturing stellar energy beyond our planet, a central challenge emerges: how to effectively deliver this energy back to Earth, where it can be harnessed for practical use. The vast distances and harsh environment of space pose significant obstacles to traditional energy transfer methods, such as physical cables or fuel transport. Instead, one of the most promising solutions lies in wireless energy transmission, a technique that could revolutionize the way we think about power distribution on a cosmic scale. By converting the collected energy, whether from photovoltaic cells stationed in orbit or more advanced stellar collectors, into directed beams of electromagnetic radiation, such as microwaves or lasers, energy can be sent across the void safely and efficiently. This approach not only circumvents the mass and fragility issues inherent in tethered systems, but also allows continuous transmission, irrespective of Earth's rotation or atmospheric conditions, provided the receiver stations are properly positioned. The concept of wireless energy transfer from space thus offers a pathway to overcome the terrestrial limitations that have long constrained our energy infrastructure, opening the door to a future where clean, abundant power flows directly from the stars to our cities below. Early demonstrations of space-based solar power systems have illuminated the potential of this technology. Photovoltaic satellites equipped with large solar arrays collect sunlight unobstructed by clouds or nightfall, converting it into electrical energy. This energy is then transformed into a focused microwave beam directed at receiving stations on Earth, where it is reconverted into electricity for distribution. The absence of atmospheric interference in space allows for near-constant energy collection, maximizing efficiency far beyond terrestrial solar farms. Moreover, the scalability of such systems means they could be expanded incrementally, matching energy demand as it grows. While the current generation of photovoltaic cells and transmission technologies are still developing, ongoing research into more efficient energy conversion materials and beam steering methods promises to enhance the feasibility and safety of wireless energy transmission. These advances suggest a future in which satellite arrays not only supplement but potentially surpass traditional energy sources, transforming the way humanity powers its civilization. Looking further ahead, the principles of wireless energy transmission may also apply to more advanced forms of stellar energy exploitation, such as controlled fusion reactors, or even fission processes derived from resources harvested in space. As fusion technology matures, compact reactors could be deployed in orbit or on lunar and asteroid bases, converting stellar materials into vast quantities of clean energy. This energy, transmitted wirelessly to Earth, could alleviate the constraints of fuel scarcity and environmental impact that accompany terrestrial power generation. Additionally, the prospect of constructing large-scale energy collectors around stars, akin to Dyson spheres, would necessitate robust and continuous energy transfer methods to maintain the flow between space and Earth. In these scenarios, wireless transmission becomes not just a convenience, but an essential component of the energy infrastructure, connecting cosmic-scale harvesters with the demands of terrestrial civilization. The integration of these technologies points toward a future where humanity's energy network extends beyond the planet, weaving together space-based generation and Earth-based consumption in a seamless continuum. The implementation of wireless energy transmission from space also invites reflection on the broader implications for global energy equity and environmental stewardship. By placing energy generation platforms in orbit, free from the geographic and ecological constraints of terrestrial power plants, the burden on Earth's ecosystems could be significantly reduced. This shift could help mitigate pollution and habitat disruption, while providing reliable power to regions currently underserved by conventional grids. Furthermore, the ability to beam energy precisely where it is needed offers the potential for highly efficient and responsive energy networks, capable of adapting to fluctuating demands without the losses associated with long-distance terrestrial transmission. However, these benefits come with challenges, including the need to ensure the safety and security of high-power beams traversing the atmosphere, and the development of international frameworks to govern the use of space-based energy assets. Addressing these considerations will be vital as humanity moves closer to realizing the promise of stellar energy transmission. The exploration of stars as a source of energy begins with the technology most familiar to us on Earth, photovoltaic cells. These devices, designed to capture sunlight and convert it directly into electricity, have revolutionized terrestrial energy generation. In the context of space-based systems, photovoltaic cells can operate with far greater efficiency, unhindered by atmospheric interference or the day-night cycle. This advantage has inspired a range of research and development endeavors aimed at harnessing the sun's power from orbit. By positioning solar arrays in space, the continuous and intense solar radiation can be converted into electrical energy and then transmitted wirelessly back to Earth. This concept, known as space solar power, promises a virtually inexhaustible and clean energy source, addressing many of the limitations associated with ground-based solar installations. The absence of weather disruptions and the ability to collect solar energy around the clock position these systems as a compelling solution for future energy demands. The initial steps in this direction have been marked by experimental efforts to validate the core technologies, laying a foundation for more ambitious projects to come. Among the leading initiatives exploring the potential of space solar power is Japan's Aerospace Exploration Agency, or JAXA. Their dedicated programs focus on demonstrating wireless power transmission from space to Earth, using small-scale satellites equipped with solar arrays and microwave transmitters. These experiments have proven critical in understanding the dynamics of beaming energy through the atmosphere safely and efficiently. Similarly, NASA has extensively studied space solar power concepts, investigating the design of large orbital platforms capable of generating gigawatts of electricity. These conceptual studies include detailed assessments of system architecture, deployment strategies, and ground receiver technologies. Together, these research efforts validate the technical feasibility of capturing and transmitting solar energy from orbit, supporting the vision of continuous, clean power delivery. They also highlight the importance of addressing engineering challenges such as beam control, thermal management, and material durability in the harsh space environment. These projects reflect a gradual but steady progression toward operational space solar power systems, with each demonstration bringing us closer to a future where energy from the stars powers our civilization. Looking beyond photovoltaic cells, scientific inquiry continues to explore more advanced methods of harnessing stellar energy, including the prospects of nuclear fission and fusion in space. While solar power relies on converting sunlight directly, nuclear processes involve harnessing the energy stored within atomic nuclei, offering a denser and potentially more controllable source of power. Fission reactors, already a mature technology on Earth, could be adapted for use in space, providing stable energy supplies for satellites, habitats, or propulsion systems. Fusion, the process powering the stars themselves, remains a tantalizing goal, promising immense energy output with minimal environmental impact. The development of fusion reactors suitable for space applications could revolutionize energy access beyond Earth, enabling long-duration missions and off-world settlements. Additionally, these nuclear technologies might serve as complementary systems to solar power, offering redundancy and flexibility in energy generation. As research advances, the integration of such high-energy sources with space-based solar arrays could unlock unprecedented possibilities for humanity's energy future among the stars. One of the most visionary concepts in stellar energy utilization is the construction of megastructures known as Dyson spheres. Proposed as a theoretical means to capture the total energy output of a star, a Dyson sphere envisions an immense shell or swarm of satellites encompassing a star, collecting its radiant energy on a scale far beyond any terrestrial capability. Though currently beyond our technological reach, the idea stimulates imagination about how future civilizations might harness the full power of their local stars. Advances in material science, robotics, and orbital assembly techniques could one day make the construction of such colossal structures feasible. In the meantime, incremental steps like large-scale space solar power stations serve as practical precursors, demonstrating the principles of energy capture and transmission at orbital scales. The pursuit of Dyson spheres also encourages interdisciplinary collaboration, blending astrophysics, engineering, and energy policy to contemplate the challenges and benefits of stellar-scale energy projects. This vision of tapping into the vast energy resources of stars continues to inspire ongoing research and innovation, marking a horizon of possibilities for humanity's long-term energy aspirations. While photovoltaic cells have long been the hallmark of harnessing stellar energy by converting sunlight directly into electricity, another compelling method lies in the realm of solar thermal power. This approach takes advantage of concentrated solar radiation, using mirrors or lenses to focus sunlight onto a small area. By intensifying the sunlight, these systems generate substantial heat, which can then be used to produce steam and drive turbines for electricity generation. Unlike photovoltaic technology, which relies on the photoelectric effect, solar thermal power taps into the fundamental thermal energy carried by photons, expanding the versatility of solar applications. This method allows for thermal energy storage, enabling electricity production even when the sun is not shining, thereby addressing one of the main intermittency challenges of solar power. The efficiency and scalability of solar thermal plants make them a promising complement to photovoltaic arrays, especially in regions with abundant direct sunlight. Moreover, innovations in heat transfer fluids and receiver designs continue to improve their performance, pushing these systems closer to economic competitiveness with traditional energy sources. This broader utilization of solar energy showcases how humanity's understanding and engineering capabilities evolve hand in hand, broadening the spectrum of ways to convert stellar emissions into usable power. Beyond terrestrial applications, the principles of solar thermal power also open intriguing possibilities for space-based energy capture. In orbit or on the moon, where sunlight is more intense and uninterrupted by atmospheric interference, concentrated solar power systems could operate at higher efficiencies. These platforms could generate vast amounts of thermal energy, which might then be converted into electricity and transmitted wirelessly to Earth, or used directly to power habitat systems and propulsion technologies. The concept of space-based solar thermal power envisions a future where energy harnessed from our nearest star supports not only planetary needs, but also deep space exploration and colonization efforts. The ability to capture and convert stellar energy in diverse environments emphasizes the adaptability of solar thermal technologies and their potential to serve as foundational elements in humanity's expanding presence in space. Continued research into materials that withstand extreme temperatures and methods to efficiently convert and transmit energy will be crucial in transforming these concepts from theoretical frameworks into operational realities. Looking further ahead, the evolution of stellar energy utilization invites consideration of more advanced processes, such as harnessing fission and ultimately fusion powered by stellar materials. While solar thermal and photovoltaic systems rely on the star's radiant energy, nuclear processes tap into the energy stored within atomic nuclei, offering dramatically higher energy densities. Fission technology, currently employed in terrestrial nuclear reactors, could one day be adapted to utilize materials mined from asteroids or even from the stellar vicinity, providing compact and powerful energy sources for deep space missions or off-world colonies. The gradual mastery of fusion, the process that powers stars themselves, promises an almost limitless energy supply, mirroring the very mechanisms of stellar energy generation. Achieving controlled fusion on a practical scale remains one of science's greatest challenges, but holds the key to unlocking an energy future that aligns closely with the fundamental processes of the stars we seek to harness. Such advancements would represent profound leaps from current solar capture methods, signaling a shift from passive energy collection to active replication and control of stellar phenomena. The pursuit of harnessing stellar energy through increasingly sophisticated means, from photovoltaic cells to solar thermal power and ultimately nuclear processes, lays the groundwork for visionary concepts like Dyson spheres. These megastructures imagine the complete encapsulation of a star's energy output, combining the principles of concentrated solar capture with advanced energy conversion and storage systems. Beyond the theoretical allure, the incremental development of scalable solar thermal plants and nuclear technologies offers tangible milestones towards such ambitious futures. Each step expands humanity's capacity to utilize the immense power of stars, fostering a continuum of innovation that bridges present capabilities with distant possibilities. As research progresses, the integration of these diverse technologies will likely catalyze new paradigms in energy generation, space exploration, and sustainable development. At the heart of every star lies a powerful process that fuels its radiant glow: nuclear fusion. This phenomenon occurs as atomic nuclei merge under extreme temperatures and pressures, releasing tremendous amounts of energy. Scientists have long sought to replicate this stellar alchemy here on Earth, aiming to create a nearly limitless, clean power source. Unlike nuclear fission, which splits heavy atoms and produces long-lived radioactive waste, fusion fuses light atoms, such as hydrogen isotopes, yielding energy with minimal environmental impact. The challenge lies in achieving and sustaining the intense conditions necessary for fusion to occur, conditions that naturally exist only in the cores of stars. Yet, advancements in magnetic confinement devices like tokamaks and inertial confinement methods have brought humanity closer to this goal. By mastering fusion, we would unlock an energy source capable of powering civilizations for millennia, drawing directly from the processes that have illuminated our universe since its inception. The path toward practical fusion energy involves intricate physics and cutting-edge engineering. Magnetic fields in devices such as tokamaks contain plasma, heated to temperatures exceeding those of the sun's center, allowing hydrogen nuclei to collide and fuse. Recent experimental successes have demonstrated net energy gain in controlled fusion reactions, a milestone that signals a new era in energy science. Parallel approaches include laser-driven fusion, where powerful beams compress fuel pellets to initiate fusion reactions. These methods promise not only abundant energy, but also a safer alternative to traditional nuclear power, as fusion reactors inherently avoid runaway chain reactions. The implications extend beyond terrestrial power plants. Fusion propulsion could revolutionize space travel by providing efficient, high-thrust engines for interplanetary missions. As research steadily advances, The dream of harnessing the sun's power on Earth inches closer to reality, offering a beacon of hope in the quest for sustainable energy. Looking further ahead, the concept of constructing megastructures around stars, such as Dyson spheres, embodies humanity's aspiration to capture stellar energy on an unprecedented scale. These hypothetical constructs envision vast arrays of solar collectors or habitats completely encompassing a star, collecting nearly all its emitted energy. While currently within the realm of theoretical engineering, the incremental mastery of fusion and solar technologies lays the foundation for such ambitious projects. The immense energy harnessed could support advanced civilizations by meeting all power needs and enabling large-scale space colonization. In this vision, fusion reactors may serve as vital components within these systems, converting stellar energy into usable forms while maintaining stability and efficiency. The gradual evolution from photovoltaic cells to fusion power and eventually to colossal star-encompassing structures illustrates a continuum of innovation where each breakthrough builds upon the last. This continuum invites us to imagine a future where the sun's energy is fully integrated into human progress, transcending earthly limitations. As we continue to explore the vast potential of harnessing stellar energy, it is essential to consider the remarkable strides made in fusion research. Fusion, the very process that powers stars, holds promise as a nearly limitless source of clean energy here on Earth. Unlike traditional nuclear fission, fusion combines light atomic nuclei, such as isotopes of hydrogen, to form heavier elements, releasing tremendous energy in the process. This reaction mimics the core processes of the sun, offering a direct parallel to the energy generation of stars themselves. For decades, scientists have pursued the challenge of achieving controlled fusion reactions that produce more energy than they consume, a milestone known as net positive energy output. Achieving this balance would mark a transformative moment in humanity's energy capabilities, providing a powerful, sustainable alternative to fossil fuels and reducing environmental impact. Among the most ambitious fusion projects is ITER, an international collaboration based in southern France, designed to demonstrate the feasibility of large-scale fusion power. ITER employs a device called a tokamak, which uses strong magnetic fields to confine hot plasma, ionized gas heated to temperatures exceeding those of the sun's core. The project aims to sustain fusion reactions long enough to produce significant net energy gain, targeting a 10-fold return on energy input. ITER represents a monumental step forward, bringing together expertise and resources from over 30 countries. Recent milestones include successful plasma generation and improvements in magnetic confinement, edging closer to steady-state fusion conditions. These advances not only validate theoretical models, but also enhance our understanding of plasma behavior under extreme conditions. The knowledge gained will inform the design of future reactors, capable of continuous operation and integration into power grids worldwide. Beyond ITER, a host of innovative approaches to fusion are under exploration. each aiming to overcome the complex engineering and scientific hurdles inherent to replicating stellar processes on Earth. Alternative concepts such as inertial confinement fusion use powerful lasers or ion beams to compress fuel pellets to extreme densities and temperatures, sparking short-lived fusion bursts. Other experimental devices explore magnetic mirror configurations or stellarators, offering different methods of plasma control. These efforts collectively contribute to a growing tapestry of knowledge and technological refinement, pushing the boundaries of what is achievable. As these experimental platforms evolve, the prospect of commercial fusion power plants, compact, safe, and efficient, becomes increasingly tangible. With sustained investment and collaboration, fusion energy promises to reshape the global energy landscape, providing a bridge between the sunlit promise of photovoltaics and the grand visions of star-encompassing megastructures. Fusion research, while complex and demanding, symbolizes humanity's deepening understanding of stellar phenomena and our ability to harness them. From the earliest photovoltaic cells that convert sunlight directly into electricity, we have steadily progressed toward more sophisticated means of tapping into stellar energy. Each step reveals new possibilities, from scaling solar arrays across planetary surfaces to developing reactors that echo the sun's inner workings. This progression hints at future innovations, where the boundaries between star and civilization may blur further. As we refine fusion technologies, we also lay the groundwork for integrating them with other advanced concepts, such as artificial photosynthesis or space-based energy collection systems. The journey from capturing photons on silicon wafers to igniting plasma within magnetic fields charts a path of expanding mastery over the forces that govern our universe. The story of nuclear fission begins deep within the hearts of stars, where the crucible of stellar nucleosynthesis forges the very elements that make up our world. Elements heavier than hydrogen and helium emerge through a series of fusion reactions in massive stars or during the cataclysmic explosions of supernovae. Among these elements are uranium and thorium, whose atomic structures possess the unique ability to undergo fission, a process where heavy atomic nuclei split into lighter nuclei, releasing a significant amount of energy. On Earth, humanity has learned to harness this primordial power through controlled nuclear reactors, tapping into the energy stored in these star-born atoms. This connection between stellar origins and terrestrial energy underscores a profound continuity, linking the vast cosmic processes that shape the universe to the daily electricity that powers human civilization. Nuclear fission reactors operate by initiating a chain reaction where neutrons released from the splitting of one atomic nucleus induce further fission events in surrounding atoms. This cascading effect releases heat, which is then converted into electrical power through turbines and generators. Unlike solar cells that rely on photons from stellar surfaces, fission taps directly into the atomic fabric created within stars millions of years ago. This method offers a dense and reliable source of energy, capable of sustaining modern societies with relatively low emissions compared to fossil fuels. Yet, the management of radioactive waste and the complexity of reactor design present ongoing challenges. Despite these hurdles, fission remains a bridge between our understanding of cosmic matter and practical energy solutions, demonstrating how elements born in stellar furnaces continue to fuel human progress here on Earth. Looking beyond terrestrial applications, The future of harnessing stellar energy extends toward more ambitious concepts, inspired by the scale and power of stars themselves. Among these is the idea of Dyson spheres, hypothetical megastructures that would envelop a star to capture a vast majority of its energy output. While still theoretical, such constructs represent the ultimate expression of humanity's aspiration to integrate directly with stellar power sources. In parallel, advancements in nuclear technology may lead to hybrid reactors that combine fission with fusion processes, optimizing efficiency and reducing waste. These developments suggest a trajectory where energy generation evolves from scattered terrestrial installations to vast, space-based systems, effectively turning stars into giant power plants. This vision invites us to reconsider our relationship with the cosmos, transforming stars from distant lights in the sky to accessible and sustainable energy reservoirs. The interplay between fission and fusion technologies, both rooted in stellar phenomena, highlights an expanding palette of energy solutions that reflect our growing cosmic perspective. While photovoltaic cells continue to improve in efficiency and scalability, the integration of nuclear processes offers complementary pathways to meet increasing energy demands. The materials used in fission reactors, forged in stellar interiors, remind us that the universe's life cycle is intricately connected to our technological endeavors. As we explore deeper into these connections, the prospect of deploying energy collection systems beyond Earth's atmosphere becomes more tangible. Space-based platforms could gather and transmit stellar energy with minimal loss, potentially revolutionizing how power is distributed across planetary colonies and Earth itself. This unfolding narrative speaks to both the ingenuity and the patience required to transform starborn resources into practical benefits for humanity. As our mastery of stellar energy sources advances, the synthesis of these approaches lays the foundation for future innovations that may redefine energy altogether. The progression from capturing sunlight on photovoltaic panels to harnessing the atomic remnants of stars through fission illustrates an evolving dialogue with the cosmos. Emerging research into artificial photosynthesis and magnetic confinement fusion may eventually converge with large-scale space engineering projects, creating an interconnected network of energy systems that span from planetary surfaces to orbital structures. This continuous expansion of our capabilities mirrors the complex, dynamic processes within stars themselves, suggesting a future where human technology harmonizes with stellar mechanics. In this ongoing journey, each discovery and invention brings us closer to an era where the vast energy of stars is not just observed or admired, but actively and sustainably utilized. The journey toward harnessing stellar energy has taken many forms, evolving from the gentle capture of sunlight with photovoltaic cells to the more intricate realm of nuclear fission, where the very essence of atomic nuclei is divided to release immense power. Next-generation fission reactors represent a significant step forward in this evolution, focusing on innovations that prioritize both safety and efficiency. Among these advancements, small modular reactors, often abbreviated as SMRs, are gaining considerable attention. Designed to be compact and factory-built, SMRs offer the potential to be deployed with much greater flexibility and at reduced costs compared to traditional large-scale reactors. Their modular nature allows for incremental capacity increases and tailored energy solutions suitable for diverse environments, from urban centers to remote locations. This modularity not only simplifies construction but also enhances safety, as these reactors are equipped with passive safety systems that minimize human intervention and reduce the risk of accidents. Alongside SMRs, thorium reactors emerge as another promising frontier in nuclear fission technology. Thorium, a more abundant and widely distributed element than uranium, offers advantages that could redefine how we approach nuclear fuel cycles. The thorium fuel cycle produces fewer long-lived radioactive waste products, which addresses one of the long-standing challenges of nuclear power: the management and disposal of hazardous materials. Moreover, thorium reactors operate at higher neutron economy, meaning they can sustain fission more efficiently, thereby extracting more energy from the fuel. These reactors also demonstrate inherent safety features, such as the potential for self-regulating reactions that reduce the risk of overheating or meltdowns. By exploring thorium as a fuel source, scientists and engineers are not only tapping into an alternative energy reservoir, but are also advancing the broader goal of creating sustainable, low-carbon energy systems that can complement renewable technologies. The development of these next-generation reactors is more than a mere technological upgrade. It represents a philosophical shift in how humanity interacts with the energy embedded within the atomic fabric of our universe. As we refine our capacity to manage fission safely and efficiently, the implications extend beyond Earth-bound applications. These innovations lay essential groundwork for future space exploration and colonization, where compact, reliable energy sources will be indispensable. The ability to generate power with minimal environmental footprint and high operational safety aligns with the broader vision of harnessing stellar energy, not only through direct collection, such as solar panels, but also through the controlled release of nuclear energy, forged in the hearts of stars. This progression draws a connective thread between the microcosm of atomic nuclei and the macrocosm of cosmic phenomena, hinting at a future where energy systems may integrate seamlessly across scales and environments. Looking further ahead, the innovations in fission technology may serve as precursors to even more ambitious endeavors, such as the construction of massive orbital structures designed to capture and utilize the full power of our Sun. Concepts like Dyson spheres, hypothetical megastructures enclosing a star to collect its energy output, remain within the realm of theoretical engineering, but inspire the continuous push toward mastering stellar energy. The advances in compact, efficient reactors could provide the initial stepping stones, powering the manufacturing and maintenance of such colossal constructs. By integrating fission technology with large-scale space engineering, humanity may one day create a network of energy generation that transcends planetary boundaries, drawing directly from the star's radiant power in ways that today seem the stuff of dreams. This dream is rooted in the steady, measured progress of today's scientific achievements, each innovation building upon the last guiding us toward a harmonious coexistence with the luminous forces that shape the cosmos. The idea of harnessing stellar energy has evolved remarkably from the humble beginnings of photovoltaic cells, which convert sunlight directly into electricity here on Earth. These cells capture just a fraction of the sun's immense output, yet they represent a profound step toward utilizing the star's energy in a clean and sustainable way. As technology advances, photovoltaic systems grow more efficient, allowing us to imagine expanding their use beyond our planet. The sun's radiant power, diffused across space, presents both a challenge and an opportunity. How might we collect more of it, and how might we do so without exhausting the resources of our homeworld? It is here that human ingenuity meets cosmic scale, inspiring visions of tapping directly into the star's full energy potential. Progressing beyond solar panels, nuclear fission offers a concentrated method of energy generation, transforming matter into vast amounts of power through carefully controlled reactions. Modern reactors symbolize a bridge between terrestrial energy needs and the more ambitious goal of stellar energy mastery. The technologies developed for fission can be adapted for use in space, where compact reactors might power spacecraft, orbital habitats, or even the construction of enormous structures in orbit. These reactors could serve as the essential tools in the assembly of megastructures designed to capture energy on a scale previously unimaginable. Through incremental steps, humanity learns to harness energy not just from the sun's light, but from the fundamental processes that govern its existence. Among the most captivating theoretical constructs is the Dyson sphere, a megastructure envisioned to enclose or surround a star completely, capturing nearly all of its energy output for use by an advanced civilization. This concept, first proposed by physicist Freeman Dyson, suggests a future where energy constraints are no longer a limiting factor. While the engineering challenges are daunting, requiring materials, precision, and scale far beyond current capabilities, the notion inspires a profound shift in perspective. Instead of merely surviving within a star's life-giving glow, such a civilization might thrive by commanding it directly. The Dyson sphere represents not only an extraordinary technological achievement, but also a cosmic leap in our relationship with the universe, transforming stars from distant sources of light to intimate engines of civilization. The path toward realizing such megastructures is likely to be gradual, built upon the steady accumulation of knowledge in astrophysics, materials science, and robotics. Fission reactors could provide the power needed to manufacture components in space, while advances in autonomous systems might allow for the precise assembly of vast orbital frameworks. These structures could begin as swarms of satellites or solar collectors orbiting the sun, gradually evolving into more continuous shells or networks. The scale of such projects is immense, demanding international collaboration and an enduring commitment to exploration. Yet, each step brings us closer to a future where the energy that fuels our civilization comes directly from the star itself, captured with elegance and purpose. As these ideas continue to develop, they remind us that the boundaries of energy generation are not fixed, but expandable, limited only by our creativity and resolve. From the simple photovoltaic cells that grace rooftops today, to the dream of enclosing a star in a shimmering sphere of technology, humanity's journey toward mastering stellar energy is as much about imagination as it is about science. This vision encourages us to look beyond the familiar, toward a cosmos filled with possibility, a future where energy flows freely from the heart of the stars, illuminating new paths of progress and discovery. The concept of harnessing a star's energy on a grand scale has inspired a variety of imaginative structures, each with its own set of possibilities and challenges. Among these, the Dyson sphere stands as a symbol of ultimate energy capture, an immense shell or network surrounding a star to intercept nearly all its radiant power. Early ideas suggested a solid shell completely encasing a star, but such a construct presents monumental engineering difficulties. The forces acting on this shell would be immense, and maintaining structural integrity without collapsing or drifting would require materials and technologies far beyond what we currently possess. Yet this vision sparked the exploration of more feasible alternatives, such as Dyson swarms, vast collections of independent satellites orbiting in coordinated patterns around the star. These smaller units could capture solar energy more flexibly, avoiding the catastrophic risks associated with a solid shell. Dyson swarms, composed of countless solar collectors or habitats, offer a modular approach to stellar energy harvesting. Each unit could operate semi-autonomously, gathering energy and transmitting it back to a central hub or directly to distant civilizations. This distributed model reduces the engineering burden of building one enormous structure and allows for gradual expansion over time. As technology advances, the swarm could grow to encompass a significant fraction of the star's output, transforming the energy economy of an entire civilization. Nevertheless, coordinating the orbits, communication, and energy transfer among so many individual elements introduces complex logistical and technological hurdles. Managing the stability of such a swarm, avoiding collisions, and optimizing energy collection efficiency will demand innovations in artificial intelligence, material science, and space engineering. Another intriguing variant is the Dyson bubble, a collection of satellites held in place not by orbital mechanics, but by the gentle pressure of the star's own light. These statites would float in a carefully balanced arrangement, using light sails to maintain position relative to the star. This approach reduces some of the dynamic complexities of orbital swarms, but introduces new challenges in controlling and stabilizing the statites against perturbations and external forces. The concept relies on the delicate interplay of radiation pressure and gravitational forces, harnessing the star's energy not only for power, but also for propulsion and positioning. The development of such technology could revolutionize how we think about large-scale space structures, enabling a more adaptable and responsive energy collection system. While these visionary structures remain beyond our current capabilities, the ongoing advances in materials engineering, robotics, and artificial intelligence steadily bring us closer to realizing them. The transition from simple photovoltaic cells, which convert sunlight into electricity on Earth, toward massive stellar energy collectors represents a profound leap in scale and ambition. Future progress in nuclear fusion and fission technologies may complement these efforts by providing efficient ways to convert and store the captured energy. In time, integrating these methods with Dyson-inspired architectures could unlock unprecedented sources of power, sustaining civilizations on scales previously imagined only in science fiction. The pursuit of such grand designs challenges us to rethink engineering principles and to innovate at the intersection of science and imagination. Each variant of Dyson's structure reveals a unique balance between ambition and practicality, inviting us to explore the possibilities of energy generation beyond traditional boundaries, whether through solid shells, swarms of satellites, or statites suspended by light itself. These concepts embody humanity's enduring quest to harness the cosmos's abundant energies. The journey forward will demand patience, ingenuity, and a deep understanding of the physical laws that govern our universe. As we continue to envision and refine these structures, we open new horizons for sustainable energy, space exploration, and the profound expansion of human presence among the stars. This ongoing exploration naturally leads us to consider the next frontier in energy generation, the fusion and fission processes that power the stars themselves. As we consider the immense scale of Dyson spheres, it becomes clear that these megastructures represent more than just a technological marvel. They symbolize a transformative leap in how a civilization might access and utilize energy on a cosmic scale. By encapsulating a star, a Dyson sphere could capture an almost unfathomable amount of energy, far surpassing the needs of any current society. This vast influx of power could fundamentally reshape the trajectory of technological and societal development, providing the foundation for advances that today seem like science fiction. Such an energy reservoir would enable unprecedented computational capacity, allowing artificial intelligence and simulations of extraordinary complexity. It could support expansive interstellar travel, terraforming projects, and the construction of habitats beyond a single planet's confines. The potential to harness the star's entire output invites us to imagine a civilization no longer constrained by energy scarcity, but empowered by abundance. The implications of accessing stellar energy extend deeply into the realms of physics and engineering. Dyson spheres, whether envisioned as rigid shells or swarms of independent collectors, would require mastery over materials science, orbital mechanics, and energy transmission on scales never before attempted. Yet, the rewards justify the challenges. A star's radiant energy captured with near total efficiency could sustain civilizations through epochs of expansion and innovation. This energy might fuel controlled nuclear fusion reactors, harnessing processes that mirror the very mechanisms powering the stars. By bridging the gap between stellar radiation and terrestrial or orbital energy systems, Dyson spheres could catalyze a shift from fossil fuels and limited renewable resources to an inexhaustible cosmic supply. Such energy abundance could alleviate many planetary constraints, fostering environmental restoration and the flourishing of life in previously uninhabitable regions. Looking further ahead, the concept of Dyson spheres invites speculation about the evolution of civilizations themselves. As societies grow in complexity and energy demands escalate, the ability to manipulate and direct stellar energy could become a hallmark of advanced intelligence. Beyond mere survival, Dyson structures could empower civilizations to manipulate matter and energy on quantum and cosmic scales, advancing fields such as particle physics, artificial life creation, and even space-time engineering. The energy surplus might enable the construction of vast computational substrates or the development of technologies that blend biology and machine, reshaping the very definition of life. This opens possibilities for virtual realities of immense depth and scale, or for establishing outposts across galaxies linked by streams of stellar energy. Such a future hints at a profound intertwining of technology and cosmic phenomena, where harnessing stars is not just an achievement, but a necessity for continued growth. While the realization of Dyson spheres remains distant, the journey towards such monumental endeavors begins with incremental steps in energy technology. Photovoltaic cells, now a common means of converting sunlight into usable power, represent the foundational technology upon which more ambitious concepts are built. As materials and efficiencies improve, solar energy will continue to be a cornerstone of sustainable development on Earth and in near-Earth orbit. Parallel to this, advancements in nuclear fission and fusion promise to unlock the processes at the heart of stars, providing compact and potent energy sources. These technologies serve as crucial intermediaries, bridging present capabilities with the dreams of harnessing entire stars. Each innovation enhances our understanding of energy conversion, storage, and transmission, setting the stage for the colossal undertakings that Dyson spheres embody. The potential impact of harnessing stellar energy extends far beyond engineering and technology. It touches on the philosophical and existential dimensions of civilization. By securing access to such abundant power, humanity and its successors might transcend many limitations that have defined previous epochs. This could herald an era where energy scarcity no longer dictates the pace of progress or the boundaries of exploration. Instead, societies could focus on knowledge, creativity, and the stewardship of life across the cosmos. The dream of building and inhabiting Dyson spheres reflects a profound aspiration to harmonize with the universe's fundamental forces, transforming stars from distant objects of wonder into partners in civilization's journey. As we move forward, this vision encourages us to deepen our commitment to scientific inquiry, innovation, and the responsible use of energy. Such reflections naturally lead us to examine the processes that power stars themselves, fusion and fission, and how mastering these might serve as stepping stones toward cosmic-scale energy solutions. The journey of harnessing stellar energy begins humbly, with the photovoltaic cells that capture the sunlight reaching Earth. These devices convert photons into electrical energy, offering a direct and tangible method of utilizing the star's radiance. Although limited by distance and the intensity of solar flux, photovoltaic technology represents the foundation of humanity's early efforts to tap into star power. As material science advances, these cells become more efficient and versatile, enabling their integration into satellites, habitats, and even exploratory crafts. Yet, this surface-level interaction with stellar energy merely scratches the vast potential held within stars. It invites us to imagine more profound methods of energy extraction, beyond the gentle touch of sunlight, moving toward harnessing the very processes that fuel stars themselves. In contemplating the next steps, scientific exploration turns to nuclear fission and fusion, the fundamental reactions that power stars and, increasingly, terrestrial reactors. Fission, the splitting of heavy atomic nuclei, has long been a practical source of energy on Earth, providing a glimpse into controlled stellar power. Fusion, the merging of light nuclei, such as hydrogen isotopes, promises a cleaner and more abundant energy source, mirroring the processes at the heart of stars. The challenge lies in recreating and sustaining these reactions efficiently and safely, a task demanding extraordinary precision and innovation. Success in fusion research would mark a significant milestone, propelling humanity closer to the dream of stellar-scale energy use. This progression not only enhances our current energy landscape, but also serves as a conceptual bridge toward grander ambitions, where controlling stellar energy becomes not just a scientific pursuit, but a defining characteristic of advanced civilizations. Beyond the confines of nuclear processes, the concept of Dyson spheres emerges as a pinnacle of energy ambition and cosmic engineering. Proposed as hypothetical megastructures enveloping a star, these spheres or swarms could capture the vast majority of a star's radiant energy, transforming it into usable power on an unimaginable scale. While such constructs remain firmly in the realm of theoretical and speculative science, they inspire questions about the technological and material capabilities required to realize them. The idea challenges our understanding of physics, engineering, and the limits of civilization's reach. It also invites us to consider the ethics and implications of altering stellar environments so profoundly. The pursuit of Dyson spheres is not merely an engineering problem, but a profound inquiry into the future of life and energy in the universe. In tandem with theoretical studies, astronomers have begun to search the cosmos for signs of Dyson sphere-like structures, linking abstract concepts with empirical investigation. These searches involve analyzing the infrared signatures and unusual luminosity patterns of distant stars, seeking anomalies that might suggest large-scale energy capture. Though no definitive evidence has yet been found, the very act of searching connects human curiosity with the vastness of space, placing the concept of Dyson spheres within the framework of scientific inquiry, rather than mere fantasy. This approach reflects a broader trend in astrophysics and SETI, the search for extraterrestrial intelligence, where hypotheses about advanced civilizations are tested through observation and data analysis. Such efforts underscore a growing recognition that the quest to harness stellar energy is as much about understanding our place in the cosmos as it is about advancing technology. As humanity contemplates the prospect of harnessing stellar energy, it becomes clear that numerous technical challenges must be carefully navigated. Photovoltaic cells, which currently convert sunlight into electricity on Earth, represent the earliest step in this journey. While these cells are efficient for capturing solar energy at a planetary scale, scaling such technology to harness the full output of a star poses formidable engineering obstacles. The harsh environment of space, with intense radiation and extreme temperatures, demands materials and designs far beyond current capabilities. Moreover, the sheer size of structures needed to capture significant energy from a star, such as vast arrays of solar collectors or orbital platforms, requires breakthroughs in manufacturing, deployment, and maintenance. These technical hurdles are compounded by the need for sustainable resource acquisition, as constructing megastructures like Dyson spheres would involve vast quantities of raw materials, potentially sourced from asteroids, moon bases, or even dismantled planets. Beyond technical feasibility, the ethical dimensions of manipulating stellar environments invite deep reflection. Stars are not merely distant energy sources. They are fundamental components of cosmic ecosystems, influencing the formation of planets and the conditions necessary for life. Altering or enclosing a star could have unforeseen consequences, potentially disrupting the delicate balance within a solar system. Questions arise about humanity's right to exert such profound control over natural celestial bodies, especially when the long-term effects remain uncertain. The concept of stewardship extends beyond Earth, inviting a broader philosophical consideration of responsibility toward the cosmos. These ethical concerns echo long-standing debates about environmental impact and resource use on Earth, magnified here on a cosmic scale. As we advance technologically, it becomes imperative to weigh the benefits of stellar energy capture against the potential risks to planetary systems and the broader universe. Looking to the future, the exploration of nuclear fission and fusion as methods to tap into stellar energy presents both promise and complexity. Fusion, the process that powers stars themselves, offers the tantalizing possibility of replicating stellar energy production in controlled environments. Success in this endeavor could provide humanity with virtually limitless clean energy without the need for large-scale stellar engineering. However, achieving and sustaining fusion reactions on Earth or in space remains a significant scientific challenge, requiring advances in plasma physics, materials science, and magnetic confinement techniques. Similarly, fission reactors, while well understood, rely on finite resources and produce radioactive waste, limiting their long-term potential as a primary energy source. The progression from photovoltaic cells to nuclear processors represents a continuum of innovation, each step requiring careful consideration of safety, sustainability, and ethical stewardship. In contemplating megastructures such as Dyson spheres, humanity confronts the scale of ambition that transcends traditional engineering and enters the realm of cosmic architecture. Constructing a Dyson sphere, or even a partial Dyson swarm, would require unprecedented coordination, resource management, and technological mastery. The ethical implications extend beyond the immediate environment to the potential impact on extraterrestrial life and the natural evolution of star systems. Would enclosing a star prevent other forms of life from emerging or evolving in that system? Could such manipulation disrupt the delicate gravitational and radiative balances that govern planetary orbits? These questions underscore the importance of interdisciplinary dialogue, integrating astrophysics, ethics, policy, and philosophy. As humanity moves closer to realizing these grand concepts, it must do so with humility and a sense of cosmic responsibility. Ultimately, the pursuit of stellar energy invites us to reconsider our relationship with the universe, not merely as passive observers, but as active participants, capable of profound influence. The challenges of technology, resource allocation, and ethical responsibility intertwine in this grand endeavor, shaping the path forward. Each step toward harnessing the power of stars demands careful thought, collaboration, and respect for the vast, intricate cosmos we inhabit. As scientific understanding deepens and capabilities evolve, the dialogue surrounding these challenges will continue, guiding humanity toward choices that honor both innovation and stewardship. This delicate balance sets the stage for future explorations of energy sources that may one day extend beyond our solar neighborhood. The journey of harnessing stellar energy begins with the technology that has become a quiet yet transformative presence in our daily lives: photovoltaic cells. These remarkable devices convert sunlight directly into electricity, bridging the vast gulf between a distant star and human needs. While the principle is elegantly simple, the implications are vast. Solar panels capture the steady stream of photons emitted by our sun, turning it into a clean, renewable source of power. As efficiency improves and costs decline, solar energy continues to permeate global infrastructure, offering a sustainable alternative to fossil fuels. This widespread adoption marks the initial stage in humanity's endeavor to tap into the immense energy reservoir offered by stars. Beyond Earth, photovoltaic arrays are also considered for lunar bases and Mars colonies, where local energy independence is paramount. These incremental steps build the foundation for more ambitious projects, reminding us that even the smallest capture of stellar energy represents a profound shift in our utilization of cosmic resources. Looking forward, the natural progression from surface-level solar harvesting leads to more complex and potent methods of energy extraction, such as nuclear fission and fusion, which draw upon the processes powering stars themselves. Fission, already a mature technology, unlocks the energy stored within atomic nuclei, providing a dense and reliable power source. Fusion, however, aspires to replicate the sun's core reactions here on Earth, promising a future where energy is abundant, clean, and virtually limitless. While the path to controlled fusion remains challenging, advances in magnetic confinement and inertial fusion research bring this vision closer to reality. Harnessing the very mechanisms of stellar energy generation would not only satisfy growing global energy demands, but also profoundly alter our relationship with the cosmos, transforming us from passive recipients of solar light to active emulators of stellar processes. This evolutionary leap embodies a deeper understanding of the physics of stars, inviting us to become engineers of cosmic energy flows rather than mere consumers. Beyond the realm of planetary technologies lies the realm of megastructures, conceptual constructs like Dyson spheres that capture the full energy output of a star. Proposed as a theoretical hallmark of advanced civilizations, these colossal shells or swarms of collectors would enclose or orbit a star, siphoning its immense radiant energy for use on a scale far beyond current human capability. The engineering challenges are profound, requiring materials science, robotics, and energy management technologies that are still in their infancy. Yet, the vision sparks profound curiosity about humanity's potential future as a spacefaring species, capable of manipulating stellar environments to sustain vast populations and complex systems. Even the smallest steps towards such megastructures would revolutionize energy availability, possibly enabling interstellar travel, planetary terraforming, or even synthetic biospheres powered directly by stellar output. These ideas inspire not only technological innovation, but also philosophical reflection on our place in the universe and the responsibilities that come with wielding such power. Each stage of stellar energy utilization reflects a gradual unfolding of human ingenuity and cosmic awareness. From the modest solar panels that sprinkle rooftops across the globe to the distant dream of enclosing entire stars, this timeline embodies a narrative of persistent innovation and expanding horizons. It is a story woven from scientific discovery, engineering prowess, and the enduring human desire to explore and thrive within the cosmos. As we stand on the cusp of these advancements, the path ahead is illuminated by both the light of our sun and the collective vision of generations to come. In the delicate dance between technology and ethics, progress and preservation, the future of stellar energy utilization invites us to imagine new possibilities while grounding ourselves in thoughtful stewardship. The journey is far from complete, and the horizon continues to beckon with mysteries yet to be unraveled. As we reflect on humanity's journey toward harnessing the power of stars, we find ourselves standing at a profound intersection of possibility and responsibility. The progression from early photovoltaic cells, those quiet panels capturing sunlight on rooftops and deserts, to more ambitious concepts such as controlled nuclear fusion, marks a remarkable evolution in our understanding and utilization of stellar energy. Photovoltaic technology, with its gentle conversion of sunlight into electricity, has become a beacon of hope for clean and accessible energy, demonstrating that even the smallest fragments of stellar power can profoundly impact daily life. Yet, our aspirations reach far beyond this initial step. Within the realm of nuclear fusion, scientists seek to replicate the very reactions that fuel our sun, promising an almost limitless, clean energy source that could redefine our relationship with power. This vision, though still in development, holds the potential to alleviate many of the energy challenges that have long burdened our civilization. Looking even further ahead, the concept of Dyson spheres invites us to imagine a future where humanity may one day capture the full radiance of a star, transforming it into a colossal engine of energy and opportunity. Although this idea remains speculative, it serves as a powerful symbol of our innate drive to explore and expand our capabilities. The notion of surrounding a star with a vast array of energy collectors reflects not only extraordinary engineering ambition, but also a deepening cosmic awareness, one where we begin to think on a stellar scale, recognizing our place within the vast universe and the resources it offers. Such grand designs challenge us to rethink the limits of technology and the ethical dimensions of our expansion, encouraging a balance between innovation and preservation. Looking even further ahead, the concept of Dyson spheres invites us to imagine a future where humanity may one day capture the full radiance of a star, transforming it into a colossal engine of energy and opportunity. Although this idea remains speculative, it serves as a powerful symbol of our innate drive to explore and expand our capabilities. The notion of surrounding a star with a vast array of energy collectors reflects not only extraordinary engineering ambition, but also a deepening cosmic awareness, one where we begin to think on a stellar scale, recognizing our place within the vast universe and the resources it offers. Such grand designs challenge us to rethink the limits of technology and the ethical dimensions of our expansion, encouraging a balance between innovation and preservation. The path to fully harnessing stellar energy is one marked by patience, curiosity, and a profound respect for the forces that govern our cosmos. Each step forward is a testament to human resilience and imagination, reminding us that the challenges we face today, climate change, resource scarcity, and energy access, can be addressed through thoughtful application of science and technology. As we continue to refine photovoltaic efficiency, master fusion reactions, and contemplate megastructures like Dyson spheres, we are also called to embrace sustainability and ethical stewardship. In doing so, we honor not only the sun that sustains life on Earth, but also the generations that will follow, inheriting the fruits of our efforts and the responsibility to nurture this planet and beyond. Ultimately, the story of harnessing stellar energy is deeply intertwined with the story of humanity itself, a narrative of hope, discovery, and the enduring quest to live in harmony with the cosmos. The stars have long inspired us, guiding explorers across oceans and igniting the imaginations of poets and scientists alike. Now they beckon us toward a future where their boundless energy may help heal our world and expand our horizons. As we move forward, may we carry with us a quiet reverence for the celestial fires that light our days, and a steadfast commitment to using their gifts wisely. In this delicate balance lies the promise of a sustainable future, one illuminated by the gentle, steady glow of the stars we have learned to embrace.